Hi, my name is Tabassum Raizada, and this is my practicum presentation on emotion classification using multimodal deep learning models. The goal here is to classify electroencephalography or EEG data using deep neural networks into various emotion states. And we will be combining EEG data with other modalities like the eye movement data or the video recording data and see the impact on the classification accuracy. Now, why is this relevant? Well, it has several clinical applications. For example, just investigate sleep patterns, for seizure prediction, consciousness and hyperactivity disorders, and also for patients in rehabilitation centers. Risk and safety applications to evaluate the mental state of doctors and healthcare workers in stressful positions, or to see the mental state of a pilot who's about to go on an important mission, because we as humans are very good at deceiving others in terms of our emotion, but really it's not possible uh, d- um, to curb those emotions on the EEG signals that are coming from our brain. It also has a lot of retail applications. An example that I state is that of Dolby Labs, who are known for producing great sound effects in cinema. They used a Nautilus Pro wearable EEG device to study emotion responses of the audience while they were watching videos. And the scientists at the labs were trying to better understand what makes the audience engage and what makes their skin blush and increase their heart rate, stuff like that. Also, in gaming, they use these applications. Um, Now, what is EEG data? The very word neuron in convolutional neural networks comes from the brain neurons, from which we are trying to collect the data here. When a neuron in a brain becomes active, there's a flow of ions that creates a spatial asymmetry resulting from the ions going in and out of the neuron. Now, when thousands of these neurons are activated at the same time, we could capture that signal by an electrode that's placed on the scalp. And what's captured really is in a time series data of these from the different electrodes placed on the brain. And they're really over here, we can see that as squiggly lines. And each segment that you see over here is like 1 second. And at different frequencies, we are capturing the data. Now, it's important to understand the word channel. Channels is where on the brain those different electrodes are placed, and it follows the international 10-20 system of placement, where the distance from the tip of the nose or to the back at the base of the brain is divided into 10 or 20% intervals. And these 2 points are the nasal and the anion points. And on this scale, every electrode has a specific name. Over here in the studies that we will be using, we have data captured across 62 channels and 32 channels. Let's go on to look at the data sets we used. So the first one is the SEED or the SJTU emotion EEG data sets from the Shanghai University. I have tried to not publish any of the data set that I was provided because we need to get specific approvals before they provide you access. So over here in this experimental setup, they use this EEG cap with the 62 electrodes to capture the data. As you can see, the subject is also wearing eye tracking glasses where they are measuring the eye movement data. And to elicit the emotion response, they are using different video recordings. In this case, these were Chinese videos which were supposed to elicit responses like happiness, sadness, fear, or just a neutral state, which is what we're going to try to classify. So the labels we have used here for classification is 0, 1, 2, 3, and 4. The second data set we used is from the Queen Mary University of London, and they have used a very similar setup to capture the emotion state of a person. Here, the labels were available across a scale of valence and arousal. We see the person wearing electrode cap here. And I believe over here we had 40 different channels, which includes the muscle data, which is not something we have used in our study here. We have just used the 32 electrodes which are placed on the brain here. So, and to understand the scale that we are using here, this is what valence and arousal looks like. Valence is more like a positive state of mind, and arousal is how excited you are. So, you could be in a high valence and a high arousal state when you're happy, excited, or pleased. And you are in a high valence, low arousal state when you're relaxed, peaceful, and calm. So we used a threshold of 5 on the scale of that was available to us, and anything more than 5 was 1. Anything less than equals to 5 was 0. So we converted it to a binary classification problem here. I do want to call out the two main papers published by the university that have captured this data that I have used for reference in building these models. Now, the first is a seat multimodal model where I have used the EEG data, and more specifically, I have used the processed EEG data, differential entropy data, that is collected for the 24 different trials that the 15 different participants went through. So each trial corresponds to a video that was shown to elicit a certain response, and each participant came back on 3 different days. And for every 1 second, we have 128 readings because we have data at 128 hertz being gathered. Okay. Now, we in our data set do have data from 62 channels, but we will not be using all of them. And also, differential entropy is calculated across 3 different frequency bands. And frequency bands are really the amplitude of the data that's being gathered. Generally, for emotion analysis, we used frequency bands that are between 50 and 4 hertz. Again, eye movement data has different measures of blink, fixation, pupillary distance, pupil size, saccade measures. So it's a really very rich data that just the eye movement is capturing based on the subject watching the video. As you can see that I'm not using any max pooling layer here because I'm using pre-processed data. So the dimensionality is greatly reduced here, and max pooling can really further reduce the dimensionality, which is not something I'm looking for here. Generally for image data where we have very high dimensionality, that works out well. And again, I flatten the data before I concatenate it and pass it through a few additional dense layers. So that's definitely more scope of improvement in this model. But let's look at what the results we got just using this. So the first run included data from 6 channels and across 3 frequency bands. The second run was using just the eye movement data. The third one was the multimodal with both EEG and eye movement data. The fourth run, I threw in data from 41 different channels and all 5 frequency bands. And the next one is with the EEG data across 41 channels along with the eye movement data. So we can see how when we move from single modality to multimodal models, there was a slight improvement because really the eye movement data seems to give a lot of good results here. Again, adding 35 different channels did not result in a great improvement. In fact, it went down in the fourth run and could just have been at that point in time. But as we can see in the last case, compared to the model 3 and 5, we see a slight improvement. So just throwing too much data at it did not really help. So as the paper said, these 6 channels, which are along the temporal channels, really give rich data for emotion state prediction classification. And if we look at the classification report from one of the models, we see that the sad emotion state has the highest recall rate. So really, the negative emotions plays show up very well in the BCI data. The second model the next model for deep is a little bit more involved. We have several pre-processing steps here. Um, one of the concepts we use is of removing the baseline signals. So in the data that's available for each trial, we have a 3-second baseline, which is a neutral state when a person is not watching any video. We break that 3-second into 1-second segments, find the mean of it, and then we use that to subtract it from the raw EEG signal, which is captured while the person is watching the video. So this just gives you the differential of what shows up in the EEG signal for that emotion state. The second important pre-processing step here is to convert a one-dimensional EEG data across the 32 different EEG channels to a 9 by 9 matrix. So we're converting one dimensional into two dimensional. And the goal is to try to capture the spatial features of the data, like where the electrodes are placed. As we saw, the electrodes placed along the ears is what we had used, and they were pretty good at predicting the emotion data. So the goal of this pre-processing step is to capture the spatial features. Now, each of the 9 by 9 matrices for the spatial data, we had breaking it down into 60 segments, one for each second of data in the trial. And we are passing that through parallel convolution neural networks with 3 convolution layers. In the end, we take sort of this 2 by 2, 9 by 9 matrix, and we concatenate it by depth to sort of convert it into a cube. And then we use 1 by 1 convolution for depth reduction. We then combine it with the LSTM results from the RNN part of the model, where we are trying to capture the temporal features of the data. In the end, we pass it through a softmax classifier for the binary classification, either to high-low valence or high-low arousal. The second model that I used was combining the EEG data from the channels that we just talked about, the temporal placement of the channels, with the video data. And again here, just like we broke it into 60 segments, we broke the video into 60 frames that corresponded to each of these segments here. So we were able to then combine these two data sets, one for the EEG spatial data and the other for the video data, to build a functional API model. This is what the results look like. The first one is for the deep hybrid model, which is using the parallel CNN and RNN layers, the valence classification with and without baseline, and the arousal classification with and without baseline. So and again, important thing to note is that we are running this by subject and not for across subjects. So we see that there's a marked improvement with and without baseline of almost 30 points in both the case of valence and arousal. So really the first pre-processing step of removing baseline data was really important in improving our results here. Looking at the second results, we see a really high rate of accuracy with the video data. Um, um, and again, there was a slight improvement when I combined it with the temporal EEG data. I do want to call out that all the studies here in deep data are subject specific, versus with the seed data where we had combined the data across subjects. And the reason that I could not run it across subject is just because of the high volume of data and not having access to unlimited resources to be able to run the models there. For example, if I had used data for all 22 subjects, and I had 2,400 data points for one subject, it would have been 52,000 plus data points for all of them. But I did try to combine a few subject data, and that did bring the accuracy down to almost 70%, and that was fairly low, but that could have slightly improved if I had combined across subjects and the model had the opportunity to learn more features and be able to generalize more. Again, all my models are available at this GitHub link. So thank you so much for listening.